So in this video, we're going to talk about how to use what's called the first derivative test. And this test will help you determine where a function is increasing or decreasing, or constant, if that happens. So first, let's get some definitions out of the way for increasing versus decreasing. Now, you've probably heard these phrases before, but we do have to get used to a more mathematical way to describe these features. So we say that a function is increasing on an interval if for any two numbers x1 and x2, just whichever two x values you're comparing, in this interval for the x values to the left, as we go towards the x values on the right, we're implying that their y values on the left are less than their y values on the right. Okay, so that implies that f of x1 would also be less than f of x2. Okay, so this is, again, just a fancy way of saying as we move on a graph, we have this x value that comes first and then this x value that comes second. If this one, again, comes first, then the y value of that one would be less than the y value of the one that comes second, which implies, of course, that the function is increasing or going up to the right. So our definition for decreasing on an interval is very similar to this. So we would say a function f is decreasing on an interval if what we can state about any two x values on the interval is that for any that come to the left versus the right, the y values are actually going to have the opposite relationship, where f of x1 would be greater than f of x2, because we're going down to the right when we have a decreasing function. Okay, so again, they aren't new concepts. We're just trying to think of them in a more mathematical manner here. So let's take a look at an example, a graphical example to start with. And I'm just doing a sketch. I'm just doing a sketch here. So what's important is the relationship between the important points I draw in here, but it does not have to look super identical because it's going to be kind of squiggly. Just gonna do something like that. Okay, and we're going to have some important points called A. Let's do that in green. And then we'll have this one called B. This one will be point C, D, and E. Okay, so again, it doesn't have to look the exact same, but that general sketch. So, I want you to tell me when is, I'm going to name this guy graph F, function F. When is F increasing? Okay, so if we take a look here, increasing means when we look left to right, our y values should be going up. So that is not the case from A to B. It is, however, the case from B to C. And I'm just going to use interval notation here. And that's not the case here or here. So that seems to be our only interval of increase. Whereas F decreasing, okay, so again, that means that our y values go down to the right. So that's the case here from A to B. Still not the case here. I'll go ahead and write this down. A to B. But it does happen a second time between D and E. So I'm just going to union that. And last but not least, where is f constant? And of course, that's going to be our flat area here at the top between C and D. Okay, so hopefully this doesn't feel new to you. Pretty straightforward. So the newer question we're thinking about here is, what is happening to the derivative of f in each of these sections? So when f is increasing here from B to C, okay, definitely increasing here, what is that slope? How would we describe the sign of that slope? I don't really care about the number because it's just a sketch, but the sign I can tell is a positive slope. So therefore the derivative would also be positive. Okay. If we look at areas of decrease, we said from A to B and from D to E. And if you look at those two sections, we could describe the slopes in both of these intervals as negative. And thus, the derivative in those intervals would also become negative or show up as a negative value. And last but not least, constant. Okay, the slope of a constant function is simply 0. So what we're going to be doing is obviously probably not having the picture most of the time and algebraically finding those derivatives and seeing what the signs are between these moments of change. Okay, so this identifying of increasing and decreasing intervals is what we call the first derivative test because of that connection the signs have with the first derivative. Okay, so this first states, let f be a function that is continuous on the closed interval a,b. Okay, and that is a very important first part that we're going to have to watch for on some of our problems. And the second part, so this should kind of sound familiar. We've had another thing we've done before that kind of started that way, hint, hint. But this new part now, since we're looking at the first derivative, is it has to be differentiable as well. On the open interval. We don't really think of endpoints as being differentiable, so they're not guaranteed to work. So we're only looking at differentiability on the open interval AB. So if we are able to show that the function is continuous on the closed interval and differentiable in the open interval, then we can make the following assumptions. So if we're able to show that the derivative is greater than 0 or positive for all the x values in a given interval, then we can also state that the function is increasing on that interval. Okay, similarly, number 2 is whenever we have a derivative value less than 0 or one that is negative for all x in a given interval, then the function is decreasing on that given interval. And obviously the interval doesn't have to be like the entire interval you start with. It could be just a piece of it. Okay. And lastly, I'm sure you can guess what the third one is. If the derivative is simply 0 for an entire interval, we now know that this means the function is constant on that interval. Okay, so this is our first derivative test. It helps us figure out what the original function is doing based on the derivative sign. Okay, so now we're going to write out our steps that we're going to take when we're doing one of these problems. Honestly, you could probably figure them out on your own, but we're going to go through them anyways. So the first step we typically will do is find the critical points. So step 1 is to find the critical points of the function, which remember is where the derivative equals 0 or is undefined on the given interval, and then use those to create a sign chart. And this is very similar to what we did with velocity and acceleration, so I don't think it'll seem too new to you when we do an example here in a second. After you do that, okay, so after step 1, we're going to use the signs of the derivatives in between these critical points to determine whether the derivative is positive and thus the function is increasing, or if the derivative values would be negative and thus the function is decreasing. And a couple clarifications. Once we find these areas of increase and decrease, we can then determine if each critical value is a maximum or a minimum or neither. So just as a reminder, a maximum would be when we have increase and then decrease. And a minimum would be when it switches from decreasing to increasing. Okay, so you'll see that is a common question or follow-up question you'll get with this test. Also, again, similar to the velocity and acceleration problems, the sign charts are not acceptable justification for your answers. So you'll have to actually state your response in words. Okay, and again, this isn't brand new, but just as a reminder, like you might say something like the function, and you don't have to write this down, I'm just giving you an example. The function is increasing on C to D, and then you would state because your sign chart helps you figure out how to explain this, because the derivative is positive, or we can make it less writing. We could say it's greater than 0 there, okay? And there's lots of ways to do this. That's just like one that is pretty common. So you would have to actually state in a sentence and use your sign chart to explain it, but just drawing a sign chart is not justifying your responses. So please be careful with that. All right, so let's jump into an example here. So find the intervals on which the function f of x equals 4x cubed minus 15x squared minus 18x plus 7 is increasing or decreasing. Also, find all local extrema and, of course, justify your response. So we're just going to hit all of it in this example here. Okay, so if you look back, all the way back over here, one thing we have to always be conscious of is this first part of the test that says that the function is continuous and differentiable on a given interval. So we need to actually address that up front. So I'm going to say f of x equals 4x cubed minus 15x squared minus 18x plus 7. And I like to go ahead and do that and, well, let me give myself some room. And the first derivative. I go ahead and find those two functions right off the bat. And I ask myself, is this guy continuous on, and they don't give us a specific interval, which means it's just negative infinity to positive infinity, and it's a polynomial, which a lot of them are, so that's always nice. So it's assumed to be continuous, and its derivative would also be continuous, and thus it's differentiable. Okay, remember differentiable basically is saying, like, is this function right here also continuous. So differentiability just means the first derivative is also continuous, which would be the case. So we can say the function f is continuous and differentiable because it's a polynomial. That's enough of an explanation, but it needs to be addressed, and it is commonly not in a free response question, so please be very careful with that. Okay, so we found our derivative already. We've shown it's continuous and differentiable. So the next thing we need to do is find the critical points. So in finding the critical points, I'm looking for when the derivative is 0 and when the derivative is undefined, if it is. Okay, and in this case, because again, it's a polynomial, it's never actually undefined, so we don't really have to worry about that one. So let's go ahead and set it equal to 0 and find where that occurs. So this looks like we're going to do some factoring. So definitely try to find a GCF here because these are pretty big numbers. So 12, 30, and 18 are all divisible by 6. So 2x squared minus 5x minus 3. And you can factor this however you like. I like to do a little square area model here. A lot of you don't like this, but you're wrong. So I'm going to put 2x squared minus 3, and so it needs to multiply to negative 6, and it needs to add to negative 5. Oh gosh, I always do this one wrong. Okay, so if it multiplies to a negative, they have to have different signs. So, 6 has to be bigger. Okay. So a 2x here, an x here, 1 minus 3. Alright, so we've got 6 times 2x plus 1 times x minus 3. So I'm getting critical points at negative 1/2 and positive 3. Alright, so this means we can now make our number line, our sign chart, as some may call it, and we're going to put the values that we just found of negative 1/2 and of positive 3 here. Okay, and so we're really using this factored form right here. Well, we don't even really care about the 6. If he were negative, we'd care though, so let's think about it. And we're using these two factors here to kind of plug in test points. So a lot of times when I'm doing these, when you look at my scratch work, what you'll see are little parentheses where I've put positives and negatives in. So like for instance, if we pick a number to the left of negative 1/2, like negative 5,000, obviously this is going to be negative, and this one will also be negative. And a negative times a negative gives me a positive for my derivative. And then looking here in the middle, obvious one to try is 0. So positive and negative, which means overall the derivative will be negative there. And then again, I just pick really big numbers here. So like 1,000 would be positive, positive. Okay. So that's what our derivative is doing. Now we're going to think about what the original function is doing as a result of this, right? So we have a positive derivative, which means it's increasing. Negative derivative means decreasing. And then positive derivative means increasing again. And so because of that, we've got a max here at negative 1/2, and we have a minimum here at 3. So now we're going to state all this stuff the appropriate way, the way they would want you to on a free response question. So we're going to say f is increasing. Oh my gosh, can't write i's for some reason. Over the interval. So it's increasing in this first interval and this last interval here. So we'll say negative infinity to negative 1/2 and 3 to positive infinity. Since, again, the sign chart isn't enough of an explanation, so I'm saying I know that's the case because the derivative, the first derivative, is greater than 0 on those intervals. Okay. Next we'll say f is decreasing over the middle interval, which is -1/2 to 3, since our derivative there is negative or less than 0. Okay, now we're going to state our relative extrema, the max and the min. So I'm going to state f has a relative max at x equals -1/2. And really the easiest way to explain this one would be since f prime changes sign so it changes, the derivative changes from a positive to a negative, so that's why we know there's max. And I'm getting lazy in writing the symbols, but you get the gist. And we'll say f has a relative minimum at x equals 3, since f prime changes sign in the opposite order from negative to positive. And this is how you will use the first derivative test, either to describe intervals of increase and decrease, or to find and explain justification for relative max and min locations, or in this case to do both. And that concludes our video lesson on the first derivative test.